I'm very pleased to introduce Kelly Holley-Bockelmann. So Kelly is at the Venderbilt University. She's an expert on N-body simulations, and in particular, the formation of supermassive black holes. She's, for the last little while, but it's probably been years, been chair of the US study group studying the US contribution to the LISA experiment. So she seems like an ideal person to get to tell us about LISA. So take it away, Kelly.
Thank you so much for joining in. I really appreciate it. I wanted to give you all a warning that I've accreted some neighbor kids in the background, so hopefully they'll be quiet, but they might not be. Anyway, if you hear some shouting, that's what that is. So, okay, I'm gonna share my screen now and talk to you a little bit about LISA, the best mission in all of the land. Let me just first let you know that, oh, actually, let me pause sharing. That the way that I usually pitch my colloquia are to like first year graduate students. And so those of you who are experts in astronomy and in gravitational wave astronomy in particular, and I know that there's some of y'all here, sorry, you're gonna hear stuff that you already know. And you can help me with the questions if you feel like it. We don't have to get all the way through the talk. My main goal is for you to learn something about LISA, and if we take as long as we take, and then I'll stop after an hour. Sorry, I just mean we'll get through. We'll get through an hour together. Okay, so now I'm going to share. All right, so I'm going to talk to you a little bit about supermassive black holes, and the most important thing I'm going to talk about is how the view of supermassive black hole birth and growth and their demographics can be probed by this new window on the universe, gravitational wave astronomy. And in particular, I'm going to tell you about LISA, which is an awesome mission. So you will love it by the end. But first, I'm going to take a big step back, and I'm going to tell you about gravitational waves. So just many of you probably know this, but bear with me. You probably have heard that matter bends space-time, and gravitational waves are essentially what happens when you have masses moving, and especially masses that are asymmetrical. They make a non-zero quadrupole moment, and they emit radiation that is basically gravity. And that ripple in space-time is a gravitational wave, okay? So moving matter makes a gravitational wave, at least if it's not perfectly spherically symmetrical. It turns out that supermassive black holes make the most ginormous gravitational waves that we know of, just because the space-time is so sharp and deep for supermassive black holes. And when they get close together, they can orbit one another at basically the speed of light. So that's a lot of energy that can get pumped into space-time. What you're gonna see here is a visualization of a simulation. So these are real data, but made to look really nice. And they will show you two equal mass black holes orbiting around one another, and the little lobes are the gravitational field and the radiation that's going to come off. So notice that it's quadrupolar. E and M, so an electron accelerating, emits radiation in a dipole. Mass that's accelerating emits radiation in a quadrupole. So there's lots of similarities between gravitational waves and electromagnetic waves in that they both travel at the speed of light. They're both because of things accelerating. And the biggest difference I can think of is that, electromagnetic waves move through space-time, and gravitational waves basically are space-time. So, all right, so I'm gonna play you this movie. So you can see as you go away, these little red things are supposed to represent the gravitational radiation that goes and permeates through the whole universe, traveling at the speed of light. What you've seen are the two black holes merging together to make one bigger black hole. Then the bigger black hole, the merger remnant, kind of oscillates for a little bit or rings down, and that also emits gravitational waves. These are incredibly loud. We've not seen them yet, and I'll tell you why in just a sec. All right, you might have already seen this too, but I'm gonna show you anyway. This is the first detection of gravitational waves done by LIGO. Thank you, LIGO. I'm going to play you, hopefully, the sound of those black holes orbiting together and then merging. And also, you're going to see the signal, the frequency of the change in space-time as a function of, as a function of time. Let's see. Okay, you got it? That is the sound of two black holes merging. Two black holes that are particularly around 40 and 30 solar masses. So if you want to be exact, it's 36 and 29 solar masses, and the remnant was 62 solar masses. So 3 solar masses of energy went into space-time and was radiated away as gravitational waves traveling through the universe for millions, billions of years until it made the gravitational wave detectors on Earth wiggle just a little bit. And there's a great story I can go on about LIGO and forever, but you have better experts than me about LIGO at your disposal. So if you're interested in that, you can ask questions by me and also ask questions of the folks that, that you work with. Okay, so this one little bloop, about 0.2 milliseconds of bloop, was amazing because we had the first direct detection of black holes merging together and the first detection of gravitational waves. And it basically opened up this whole new window to the universe and made, in one fell swoop, a brand new field. This field called gravitational wave astronomy. I'm part of that field. Lots of other folks are too, but it's taking advantage of this new way of gathering information from the universe. So basically light, I always think of light as kind of really distracted. So from the source, a photon will come out and it sees another photon and it interacts, or sees another particle and interacts and gets absorbed and emitted and scattered. And so the direct information from the source is kind of muddled because, again, photons are easily interacting with other photons. But gravitational waves can travel directly from the source without being scattered by photons or dust or anything. So you get a really beautiful view of the dynamics of the mass distribution that made the gravitational wave. So you get cool information about masses and distances, eccentricities and spins. And those things are really hard to get accurately with electromagnetic radiation. So it's this wonderful complementary piece of information that we've never been able to get. Okay, I'm very privileged to be able to show you this. Some of you who are, sort of like the news or like LIGO probably have seen this, but this is brand new. It was released today. This is the 03 catalog, or sort of the third science run, results plunked together with all the prior results. So we saw one black hole merger earlier, and now after the 3 episodes of observations, we have this family of black holes, of neutron stars. My cursor is, well, okay, it's easy. The blue ones are discovered by gravitational waves, particularly by LIGO. The purple ones are those that are discovered through electromagnetic means. And, I'll just concentrate on the black holes. The coolest thing that you can see is that not only does LIGO/Virgo probe black holes in a very accurate way, but they seem to probe a different population of more massive black holes than we ever thought existed electromagnetically. Actually, like 10 years ago, probably, if I were to build some sort of stellar population model of the galaxy, I would probably make all my black holes 10 solar masses, because that was the canonical, yeah, black holes are around 10 solar masses. Well, oh my goodness, no. We can have black holes that are now, 160 solar masses that we've directly seen. And so basically from LIGO's first observation, we have a conundrum, which is how do you get black holes that are this massive? So there's a beautiful problem that folks can work on in this field, and there's lots of answers, well, lots of theories right about now. Stay tuned to that. Okay, so that's LIGO. Oops. Let me see, I've lost my cursor, but that's okay. I want to show you over on your right, the purple stuff happens to be the wavelength regime, or the frequency regime, or the orbital period regime, however you like to think about it, of the LIGO detections. So the arms of LIGO, that I always like to think about it like the wavelength. The wavelength of the gravitational wave sort of fits in to this 4-kilometer arms, which are great, enormous, but what that's able to detect is changes of the matter on scales of milliseconds. So it catches the last instant of 2 black holes merging, which is wonderful, but that is kind of like only being able to see the sky in gamma rays. There's a lot more going on with the other photons, and indeed we think there's a lot more going on with the other parts of the gravitational wave spectrum, none of which has been observed yet. So when they are, we will get, we will have just as big a paradigm shift as if you were to view the world instead of in gamma rays in optical, right? I'm going to talk to you about the thing I've highlighted, this little orange thing, which is space interferometry. So again, if we want to observe things that orbit one another on timescales of a couple hours, then we need to build longer arms. The wavelength is longer, and so that's what LISA's designed to do. It's designed to probe objects that are changing their mass distribution on timescales of hours. And it turns out there's a ton of objects that we know about, and maybe probably stuff we don't know about in that wavelength regime. So to probe that, we have a mission called LISA. It's run by ESA, and NASA is a big partner, but a junior partner of the mission. And it has been selected by ESA to basically launch. So it's going to happen. If you have friends that know about LISA and are saying, is it really going to happen? Yes, it's happening. It's already been selected, and it's expected to launch in about 2034, which sounds like forever away, but you have to build an instrument, and a lot of times the folks that do build the instruments and do the data analysis and do the background foundational science think, oh, how am I going to get ready for LISA? I'm going to show you a cool little movie of LISA. So it's got sound. I'll just let you hear the sound. It sounds, So there are 3 little spacecraft that each independently carry a little mass distribution. What we're seeing is one of the nodes of LIGO. It's like an interferometer, but it's built in a triangle shape, as you'll see. So you're seeing a laser shoot from one side of the triangle to another. It's being captured by the second I think it's like 60 degrees with these 5 million kilometers. So you can see as that tumbles a little bit, the triangle tumbles, it's fantastic to be able to get better resolution on the side of your object. You're seeing it's the laser cuts. So great. But here's the key. That little cube is a free floating test mass. It is orbiting around the sun. There are 3 of them. And anytime a gravitational wave passes by, those little cubes will wiggle a little bit. And when they wiggle a little bit, you can tell the difference between the light travel time. And then if it happens in a certain pattern, you know a gravitational wave has passed.
Sorry to interrupt, Kelly, but
Of course,
the sound drowned out some of that. So it was a little hard to hear some of it. So you may want to repeat briefly.
Oh, sure. Sorry about that. So what LISA does is it has basically 5 million kilometer arms, and all it is it's a whole bunch of fancy stuff, but the main key is that there's a little heavy cube in each of the nodes, and if a gravitational wave passes by, the cube moves a little bit, okay? And if it moves in a certain pattern, then the light travel time is different between each of the arms. And there's a characteristic way that the gravitational waves will have that happen, and then you can tell that a gravitational wave is passed. Does that make sense? Hopefully. Okay, I'm gonna go on, but there will be a pause point in just a second. Okay, so that sounds like a really complicated experiment, lasers in space, by the way, the laser starts at about 2 watts. It's not like kilowatts or anything. It's a tiny little laser, so it's a very sensitive telescope as well to be able to detect the light. But the biggest question that folks thought about before LISA flew was, can you hold a test mass, the cube, can you hold it still? I mean, there could be solar wind that would push against the spacecraft, and then the test mass could move just because there's solar particles hitting it. So the question was, can you hold 3 objects still in space? Well, we couldn't answer that part, but we can send up a Pathfinder mission called the LISA Pathfinder that will test that exact thing about 1 test mass. Can you hold 1 test mass very still? Okay. All it was designed to do, really, it can't detect gravitational waves, and it didn't. But that line up at the top was what folks thought LISA Pathfinder could do. It's a mission that went up and collected data, and the axes, let's just think about the axes as how well you can hold the spacecraft still as a function of frequency. Well, the requirements of the Pathfinder is the first line. The requirements for LISA is that second line that's very thin. And the last line that has wiggles on it is the data. So, oh man, LISA Pathfinder showed that we have the technology to hold matter still much better than what we expected. And we definitely showed that LISA technologically can be a go in terms of this technology. So the big deal is, what will LISA, once it's launched, what kinds of things can we expect? And, we can expect the unexpected because it's a whole new window, it's a whole new wave band. And every time astronomers have opened a new wave band to the universe, we've totally renovated and changed our view. So here's what we think we'll see. I'm going to keep coming back to this, so let me just kind of walk through what we're seeing. The vertical axis is basically the change in space-time. So think about it as the amplitude of that gravitational wave, okay, as a function of frequency. And the little red curve, the one with the wiggles on the other side, that is the sensitivity of LISA. And so anything above that, we would expect LISA to be able to see. And then all the things in there are different categories of objects that, that can be seen, color-coded by their signal to noise. And so you might notice that, you know, the color bar goes from 1, which is not so well discovered, but all the way up to a couple hundred. So expect really loud sources here. Okay. And so the discovery space I'll walk you through. Oh, but let me just say, the first class of objects are actually those lines with the little squares. Those are black holes, supermassive black holes that are merging together. And they start out at low frequency because the objects are really far apart. Then they lose or emit gravitational radiation. And so they can get closer together, which allows them to orbit faster, which usually makes them make more gravitational waves. And so you see, this is what you would see for 2 10⁷ solar mass black holes at redshift 3 at a month to an hour before merge. And you can see that at the time of merger, you accumulate a big signal to noise. And you can see these objects a month ahead of time, which is fabulous if you want to, you know, look at it with optical telescopes or other kinds of telescopes. And if you want to accumulate a lot of data about that last month of the black hole binary's life. So those tracks are so high above the sensitivity curve that we definitely think we're going to see those if they exist. So let me back up. Sorry. We know for sure that at the center of our galaxy and of most galaxies, there are supermassive black holes. And so this is a lovely image from Nobel Prize winning group Andrea Ghez, which shows individual stars and their tracks right around this invisible object. What I love to see how when you reach pericenter, those orbits go whipping around? Well, that's because there's a ton of mass in this tiny little enclosed area. So after many years and very careful star tracking, they've been able to model what this what that mass is. And it's roughly 4 solar masses at the center of our galaxy. And the pericenters or separation between some of those stars and the black hole is small enough that we've ruled out lots of other things like just matter packed together pretty tightly, but not a black hole. So the densities are such that it's a black hole as far as we can tell. It's not the event horizon, but it's very close. Close enough for relativity to matter right there. Oh, and just in case, oh yay, I got my cursor back. You can see the center of the galaxy is right about here. And in the heart of that dust enshrouded place are stars that are orbiting this black hole. And so as we've continued to observe with individual tracers, like sometimes stars, sometimes gas, sometimes masers, we've been able to measure masses of black holes and nearby galaxies. And what folks have found is basically every galaxy has a supermassive black hole at the center. Not everyone, but basically everyone. And when you're in a new field in astronomy, it's so common to do this. It's really great. You want to know what the underlying physics is, but you can't do a direct experiment. So what astronomers do is they tend to plot one variable against every other possible variable that they can think of. And the one that gives the tightest correlation has the best signal from the underlying physics. And this is that correlation. It's the tightest correlation we know of, which is the mass of the supermassive black hole, this is in solar masses, against the velocity dispersion of the galaxy, which is just sort of like the disorderedness of the stellar velocities around the center. This is measured, though, at what is called, well, I'll just call it the edge of the galaxy. It's not actually the edge, but let's just say it's the edge of the galaxy. It's close enough. Okay, so disorderedness in stellar motion at the edge of the galaxy versus mass. And these colors are the different galaxy types, and the little ellipses are the 1 sigma error bars in those measurements. I love when I do that, because there will be a relativist in the audience or someone who does very precision work, and they'll stop me and they'll say, there's order of magnitude error bars here. And that's welcome to astronomy. We get order of magnitude error bars sometimes. It's not like we're being lazy. These are just incredibly hard measurements to make. And so, factors of 2, at least in the mass of these black holes, is not unheard of. I also like to point out the Milky Way here, because the mass is pretty well known. It's actually even known better than this, because this is an old plot. But the velocity dispersion is the tough thing to measure because we're in it. So, so it's very hard to actually measure accurately. Okay, so this is the best signal of what's going on with supermassive black holes and their underlying galaxies. But the kicker here is that, sort of the black holeness part of a 10 to the 6 solar mass black hole is, about the size of the solar system. So that's where relativity starts. It's not exactly, but it's of the order of where these black holes are. The radius of influence of a black hole of 10 to the 6 solar mass black hole is about a parsec. That's where the potential of the black hole dominates over the dark matter and the stars. The place where we're measuring the velocity dispersion is way at the edge of the galaxy, a kiloparsec away, 9 orders of magnitude away from where the black holeness is. So the big question is how does the black hole influence the motion of the stars at the edge? And so there's theories behind that. I'm not going to go into them today, but a big question nowadays is, what is the coevolution of galaxies and their supermassive black holes? Because what we think happens is that they co-evolve and they're set in their galaxies early on. In fact, if every galaxy has a supermassive black hole at the center, and we also know that galaxies grow by slamming together, merging together, then we know probably, just sort of logically, that the black holes must merge. And so here is a little, because it's a nice movie, of the assembly of I think it's a Milky Way sized galaxy, but I don't exactly remember. You'll see the gas on this side, and it's color coded according to the surface density. And these are the stars that are formed. And this simulation, you'll see, we kind of zoom around it just to show the structure is very filamentary. And as time evolves, this is the redshift. As time evolves, the galaxies kind of merge together. It looks quite chaotic. See, these guys are merging together. Well, they're flying by, sorry. But this whole system will eventually form, I think, an elliptical galaxy. So yeah, you're seeing a whole bunch of galaxies here, each of which we think has a supermassive black hole that's tied to the mass / dynamics of the galaxy, all merging together in sort of this messy system, beautifully messy system. And you may have noticed, let me turn this back, that this blue stuff is what is known as feedback from the black hole. So when these black holes merge, at least we think, some of the energy and gas gets blown out. And so this is very low density gas that's kind of blown out from the black hole. And the current prevailing theory is that's why, see that little poof, that was 2 black holes merging together, and the feedback from that merger and huge accretion event blew out some gas. Notice that the gas would be very disordered right around here. And so if stars were to therefore form out of this gas, the stars themselves would be very disordered in terms of their velocity. So that's a current prevailing theory. It's not perfectly correct about why the galaxy stellar orbits are connected to the black hole. Okay, but the big deal is, we haven't seen this process. Galaxy mergers take billions of years. Black hole mergers also take a long time to sink towards the center, we think. We've never seen this process. So LISA will be amazing to be able to detect these mergers throughout the universe. So this is kind of my drop the mic plot when I talk to astronomers. What you're seeing is the redshift on the side, or you can do the other side and say it is the luminosity distance. And the horizontal axis is the mass, total mass of two black holes that are equal mass, I think, that merge together. And the little contours are signal to noise ratio. So this is, these little triangles at the bottom are as far as we've probed so far in the universe with what we have. So you can see signal to noise ratios of like 2000 for roughly Milky Way mass black holes. See, that's 10 to the 6th. The neat thing is that you can see these black holes, if they exist and if they merge together, all the way back to redshift 20 with signal to noise ratio of a couple hundred. That is amazing, because these things will be screaming loud in the early universe. And note that cosmic dawn thing that I wrote. Okay, that is a place where photons can't really probe, because this is the epoch before reionization. So any photon that's hanging around will want to interact with a neutral hydrogen atom and reionize it. So the photons from that epoch never get to us. So we can't really know what's happening there. So a lot of the early growth and assembly of black holes, totally shrouded from our point of view. But LISA will be able to detect them and detect really loudly anything that's happening in the reionization epoch. And that is amazing. So supermassive black holes are going to be the mainstay, key source of LISA. But that's not the only thing LISA will see. There are, we think, around 10 to the 7 white dwarf binaries, neutron star binaries, basically dead stellar binary systems peppered throughout the galaxy. And we've seen some of them electromagnetically, but very close. LISA will be able to, in theory, detect all 10 to the 7 of them, because even the other side of the galaxy, you can see these objects and dust never causes you a problem. So what you're seeing there on the bottom are, sort of the confusion noise from 10 to the 7 white dwarf binaries in our galaxy. You can see those black dots with the circles around them. Those are known objects, if I remember right. And the signal to noise ratio is kind of low compared to a supermassive black hole, but yeah, you can get to the 10s to 50s for many of these. And you're going to hear a talk, I think, from Katie Brevik pretty soon, and she is an expert about this LISA topic. And so, if you love LISA and you want to hear more about that, you are in luck, because she's coming in a few weeks, if I remember right. The neat thing about these is that they'll pepper the galaxy. So you could make a map of where the white dwarf binaries are and learn something about our galactic structure. Oh, sorry. Gravitational waves are unaffected by dust. So yes, we will see all of them. Okay, so what do you want to do if you're able to see white dwarf binaries? Well, first of all, the late stage stellar evolution of binaries is really not well constrained. So we can determine things like the accretion physics, and especially during that last phase of stellar evolution where mass is exchanging from one star to another and winds are coming off. So you can use some of the data from LISA to help make that more clear. And yeah, I said mapping the old stellar population of the Milky Way. Yep, you can make a map. And essentially, we only have a few electromagnetic observations of white dwarf systems. And this will give you a ton. So more data will give us more science, more problems, but also more excitement. Okay, this is kind of cool. You remember the first LIGO black hole, the bloop that I showed you? Well, those black holes, if you dial back time and go 10 years before their actual merger, they'll be far enough apart that they'll orbit slowly enough to be able to be seen by LISA. And so that's what this figure is. It shows you tracks of black holes of that mass at different distances, but kind of close-ish to us. 10 years, 1 year, a couple hours before merger. And the neat thing about this is that I can see something 10 years before merger, get its parameters really well, because we'll be observing it for a long, long time. And then tell LIGO and electromagnetic observers right there is where you want to look at this time. And that should be able to test theories about, whether there's any kind of mass around these black holes that are also, changing the orbit, whether there's a triple black hole, etc. So this will be really neat to be able to do multi-band astrophysics. Okay, there's one more class that I think I'm going to talk about, which is those little tracks. The arrow is pointing at them. They're little arc shapes. Those are what is called EMRIs, or extreme mass ratio inspirals. And what that is basically a supermassive black hole, and then like a little stellar mass black hole, or sometimes a white dwarf or a neutron star orbiting around the supermassive black hole. It turns out that that'll emit gravitational waves in just the right frequency regime to be able to be seen by LISA. These are related to what is called tidal disruption events, which is when a star actually orbits close enough to a black hole, but it gets ripped up because the density is not so high. So we've already seen TDEs, tidal disruption events. We've never seen an EMRI. Okay, I'm going to stop here just in case. Okay, let's move on. Oh, I wanted to show you, though, a movie of an EMRI. They're so neat. Okay, what you're seeing is you're seeing a supermassive black hole. None of these objects are spinning. And then a small black hole orbiting around. This is 114 days before the merger. The little black hole is moving at a third the speed of light. And that roar you just heard was the sound of the gravitational waves being emitted. It doesn't actually be, it's not actually a sound, but they translated the frequency evolution into a sound so we can hear it. What you're seeing is this complex structure, not Keplerian orbits. It maps space-time really well because these things can last, well, you can see for a year, orbiting around basically in every direction. So you can get this lovely map of space-time right around a black hole to see if there's any weirdness that we never thought of. Oh, yeah, so we're going to see that happiness here. You look down the spin axis. Sorry, it's just really neat. And then we're going to start again. And you'll hear the sound go up a little bit. And that's because gravitational waves have been emitted. And these, and then the orbit is faster. The orbital period is faster. Ooh, did you hear that ringing? That ringing is because every so often you'll hit this gorgeous resonance. So this is a resonant orbit, and I just think they're neat. So yeah, mapping space-time and all that, but they're also just really neat. Notice we're 40% of the speed of light now. I'm just going to zip ahead to right. And that's when it merged. So you heard the chirp, and that's because the black hole is in one orbit, it loses enough gravitational radiation to basically move to a much closer orbit. So anyway, that's what an MRI does. And Lisa will be able to use it to map space-time around a supermassive black hole. Okay. Alrighty. You can also do cosmology with black holes that are supermassive black holes. So the neat thing about black hole mergers themselves is that encoded in that strain curve is the mass of the black hole. And that's the amplitude. And you can also measure the distance really well to the black hole. So you get distance in terms of meters, and you get mass. But if you had an electromagnetic observation, what you typically get is redshift. So what you can make is this great plot of meters, distance to the black hole as a function of redshift, and that slope is the Hubble constant. And so the neat thing is you can have nearby LIGO type black holes, like the 30 solar mass ones that we saw. You can have the MRIs kind of in the middle out to redshift 1, about 6 billion years after the Big Bang, to probe sort of the middle. And the massive black holes can probe very far away, even into places where light can't see or see very well. Okay, we're pretty close to the end, and I want to leave time for questions. So let me end with this. We didn't actually get into the research that I do, but if you're interested, we can talk about it. What I want to leave you with is imagine a future where instead of not knowing the distance to an extragalactic object to within a factor of 2, sometimes 10, imagine if you got distances and you knew the distance to an object to 3% or better. Imagine if you knew the mass of an object to within 1%. Remember how I showed you the supermassive black holes and they had order of magnitude error bars? That's not going to happen if you see a merging black hole with LISA. The masses are determined exquisitely. If you knew the spins of a black hole, we think black holes spin, but astrophysicists have a really hard time measuring it with photons. And you can measure it much better with gravitational waves. You may have seen some of the spins come out of LIGO, but LIGO only catches that last little bit. LISA will be able to see the merger for a month ahead of time. So we'll be able to accumulate a lot of information about the spin. We'll know spins of black holes. The one thing that you can't get super well compared to an E&M observation is the localization on the sky. So we will see on the order of a few arc minutes, sorry, an arc minute is 1/60th of a degree, sorry about that, anywhere up to 10 degrees, which is much bigger than the patch of the moon. So we don't get localization very well, but we do get information about the dynamics, the masses, the distances, the spins, and that is something we don't get through light. And so imagine, astronomers, what you could do with that information. And I'll just, make an analogy to Gaia now, which is this great space satellite that determines distances to stars in our galaxy. We're finding all kinds of new things about our galaxy, like it has a warp, etc., all because we know the distances now exquisitely because of the Space Telescope. So anyway, discoveries are in store. And with that, I think I'll end so there's time for questions.
Great, thanks.